Okay. So up to this point, we've been kind of going through some background, and we'll continue that through the rest of this class and probably into the next one as well. Now, we talked about magma a minute ago, and we're going to ignore water as magma now for a little bit, even though I consider it to be magma. Most of the volcanoes that we're going to discuss in this class are going to be silicate-based. Silicates are the most common rock type, not only on Earth, but in the solar system as well. So this is the rock type that is most likely going to be melted. So magma itself has 4 different parts to it. And each of these components plays a role in how volcanoes behave and how different volcanic products erupt. So generally, we have magmas that consist of 4 different components. Melted minerals, and for the most part, we're talking about silicate minerals. We have some solid minerals. If you go to Hawaii, the magma temperatures there are about 1150 degrees C. It's pretty damn hot. But there are minerals like olivine that have melting temperatures that are another 100 degrees higher than that. So if you're able to look at that red runny stuff up close, you'd actually see little tiny green minerals in it. And when it does finally come to rest and cool, you see nice black basalt with little green olivine phenocrysts in it. In fact, so much so that there are places on the Big Island of Hawaii where they have green sand beaches. It's mostly olivine crystals. Pretty interesting, pretty neat. Gas is another component. Most volcanoes are driven by gas. Most magmas, when they exist deep beneath the ground, have about 5% gas. If you look at basaltic magmas, the stuff we have in Hawaii, they have about 5% gas when they're buried deep in the ground. And if you look at silicic magmas, stuff that you find along continental margins like Mount St. Helens, they have about 5% gas deep down as well. And then the last part are xenoliths. What are xenoliths? What does xeno mean?
I totally forget this term and I do it every time it comes around.
You may have heard of xenophobia. You know, it's things that are different, right? These are, in a geology term, what's lith mean? What does lith mean? Rock. Xeno is foreign rock. Basically, they're hitchhikers. They're little pieces of solid rock that get plucked by moving magma as it moves up to the surface. So it's just pieces of rock that fall off the magma chamber and off the conduit walls. Some magmas have more than others, but I've yet to find any volcanic rock that doesn't have some xenoliths in it. Usually somewhere around 2 to 3%. Now the xenoliths that you find in Hawaii are really interesting because the magmas in Hawaii originate in the upper mantle. Have humans ever been to the mantle? I have a piece of the mantle in my office. We haven't been able to dig down that far. We've never drilled that far. But you can go to Hawaii and find pieces of the mantle all over the place because they're brought up as xenoliths by this magma that is created in the upper mantle. And they're solid chunks of olivine. Pretty cool. I'll bring one in next time. So those are the 4 components of magma. And all of them play a role in how the magma behaves and how it erupts. So let's start with the first part, the melted rock, okay? Now again, we're talking about silicate rock. So we're going to take a minute and review what a silicate mineral is. Now, if you've had petrology or mineralogy, this is probably more ingrained and fresh in your mind. And if you've only had basic physical geology, this concept may be a little fuzzy. And that's okay. We'll spend a few minutes going through it. Here on Earth, and actually all of the what we call terrestrial planets, the inner planets, Mercury, Venus, Earth, Mars, and our moon, they're all made primarily of silicate minerals. Silicate minerals are the most common group of minerals on Earth, because they are made of the two most common elements in the Earth's crust, silicon and oxygen. And actually, it's the most common elements in the Earth's mantle as well. Taken together, the crust and the mantle form most of the Earth. So these are the two most dominant elements we have, and they like each other. They're very compatible with each other. Silicon and oxygen love to bond together. You've heard biologists say life is carbon-based, right? Most of our cells have carbon at the heart of it. Earth is silica-based. When oxygen and silicon bond together, it forms a molecule called silica. And that is the basic building block for all of the minerals, most of the minerals in the Earth. So here's the most common elements in the Earth crust, just as kind of a review. Oxygen, 46%. I have a gigantic piece of obsidian in my office. Got them all over my yard too. And actually there's a big hunk of granite over there as well. Almost half of that hunk of granite and almost half of that piece of obsidian, and in fact half of just about any volcanic or intrusive rock you can find, it's made of oxygen. When you ask people, where do you find oxygen? They almost say, oh, in the atmosphere, it's stuff we breathe. The atmosphere only has about 20% oxygen. There's actually way more of it in rocks. And you can liberate breathable oxygen from rocks. It's possible to do this. A friend of mine in grad school, that was his master's thesis, was trying to figure out how do we take rocks that are silicate-based and liberate breathable oxygen so that we can go to planets like Mars, go to a place like the moon, and generate breathable oxygen for eventual human habitation. And he came up with this great way of doing it with fluorine gas. The problem is fluorine gas is one of the most explosive gases we have. Every time he did his experiments, they'd have to evacuate the building because they were worried about it blowing up. So at some point we'll have to come up with a better way to do it than using fluorine gas. But if we go to Mars, there's plenty of oxygen there. It's just all bound up in the rocks. You just have to find a good process for getting it out. The second most abundant element is silicon. So anytime you look at a rock, especially, if you're looking at a volcanic rock or an intrusive igneous rock like granite or gabbro, 3/4 of it made of just two elements, mostly oxygen and then silicon. And then there's the other major ones, aluminum, iron, calcium. Everything else on that periodic table that you can find out in nature combined only accounts for about 9% of the rocks in the Earth's crust. And if you go into the mantle, it's even simpler. Again, lots of oxygen and silica. So the Earth is silicate-based. So we're going to talk a little about that molecule and how we melt it and how it affects volcanic behavior. You guys have any questions so far? Okay. There is a silica tetrahedron. That is the basic building block for almost all of the magmas that we're going to talk about in this class. Like I said before, even though I consider water to be magma, we're not going to spend too much time talking about it as magma. The magmas you see coming out of places like Mount St. Helens, or Hawaii, or Yellowstone, this is at the heart of all the rocks that are produced and all the magma that comes out. So a silica tetrahedron is pretty simple. It's got a silicon atom in the middle, and it's surrounded by 4 oxygen. Now out in nature, most atoms exist as ions. You guys remember what an ion is? From your chemistry class that you either had here or back in high school. What's an ion?
I was going to say a light particle.
It's an atom that has a charge. Positive charge is called a cation.
And anion is negative.
Anion is negative. You know, there's cat people and there's dog people. I'm a cat person. Cats are positive. There's a negative associated with an an in my life, but we won't go there. All right. So, if you look at the charges on these things, we have a +4 silicon in the middle. Out in nature, silicon most commonly exists as a +4 cation. That's just what it likes to be out there in nature. Oxygens out in nature love to be -2 anions. So if you take a +4 silicon and surround it with 4 -2 oxygens, what's the overall charge? +4, -2, -2, -2, -2. You add them all up and you get a -4 charge. Okay? Do things like being charged out in nature for very long? They're going to attract things, right? What is this going to attract? It's going to attract 4 positive charges. So you have a -4 overall charge to the tetrahedron. That's where the term tetrahedron comes from. Kind of looks like a 4-sided pyramid. But since it has that -4 overall charge, it's going to attract some cations. So it can attract a +2 iron, and maybe a +2 magnesium, or maybe a +3 iron and a +1 sodium, or a +1 potassium. It's going to try to balance itself out by attracting cations. It can also balance out its charge by doing something that we call polymerization. Polymerization is a chemistry term for repeating a molecule again and again and again. So what I want to do, it's easier for me to do this on the board than by PowerPoint. So let's just take what we know so far and let's build a tetrahedron. What goes in the middle? Silicon. What's the charge? +4. Now it's got 4. This ... is kind of going off into the background. What's surrounding it? Oxygens that have a -2 charge. There's 4 of them. Now what's the overall charge? -4. And we talked about you could stick in a couple of, let's see, irons. What's the chemical formula for that molecule? Fe2, SiO, and all charges are balanced out, right? You guys know what mineral that is? That's an olivine mineral. It's a very simple silicate mineral. You could also replace this with magnesium. And then you get FeMg, which is another variety of olivine. Okay? So that's just one way of making a mineral. But the other thing that can happen is you can go through this process of polymerization, which means that we're going to repeat this molecule again and again. So let's take this oxygen right here and we'll polymerize it. So we're going to make another tetrahedron here. So we have an Si in the middle, right? And we're surrounded with 4 oxygens. In this case, we're sharing this oxygen between 2 tetrahedron, aren't we? Okay? Well, guess what? I can do the same thing here. Do an Si to now on this tetrahedron, how many oxygen have we shared? 2, right? And we could do that to these 2 as well. I'm not going to draw them out, but we can have tetrahedron that are sharing all the oxygens. When you share an oxygen between 2 molecules, not only do you share the atom itself, but you're sharing the charge. Okay? So this is a -2 charge. In order to balance everything out, a -1 charge will be tied to that tetrahedron, and the other charge will be tied to this tetrahedron. Okay? What if we do that at all 4 corners? What becomes the overall charge on this tetrahedron here in the middle? You have a +4 in the middle, right? What does this oxygen contribute? -1. What does this one contribute? -1, -1, -1. What's the overall charge? It's all balanced out, right? And if you do this in 3 dimensions, billions of time, you have the silicon here, you have 4 oxygens, but those oxygens are being shared with another tetrahedron. The formula becomes not SiO4, but SiO2 because you're sharing all of these. What is this mineral? Quartz. That's what quartz is. Quartz is just silica that's been polymerized in 3 dimensions and has no cations. It's just tetrahedron. Okay? The other thing that you should know for this class is that all these bonds right here are really, really strong. Super strong bonds. How do you break a super strong bond?
A lot of energy.
A lot of energy, a lot of heat. Why are magmas so hot? They have to be to break these really, really strong bonds. Melting temperatures on this are 700 to 800 degrees C. That's really hot. Go home, turn on your self-cleaning oven that gets up to 550, 600 degrees Fahrenheit. Go ahead and stick your head in there for a while. It's nowhere close to the heat needed to melt this stuff. This is closer to 2,000 degrees Fahrenheit. So these bonds are really strong. So magmas require an awful lot of heat to start breaking these bonds. Okay, so you can balance tetrahedron with cations, or you can polymerize them. In every case, though, the bonds are really strong. Okay? Require a lot of heat. That's why magmas are so damn hot. And polymerization can take on many forms. You can have some that aren't polymerized at all. Remember that olivine example I gave you? None of the corner oxygens were being shared. Okay? You can have chain silicates where, look at this tetrahedron here, where you have 2 oxygens that are being shared and 2 that aren't. You can have double chains. Sometimes there's 3 being shared, sometimes there's 2. Sheet silicates. Big extensive sheets. How many of you have seen muscovite, biotite? The bonds that hold the sheets, the bonds within the sheets are very strong. The bonds between the sheets, very weak. That's why you get the basal cleavage with sheet silicates. And then finally, I can't draw it very well, as you can see on the board. This diagram didn't draw it very well either. You can have all the oxygen shared and you get this really elaborate 3-dimensional sharing of all the tetrahedron that you get in quartz.
Sorry, I was just remembering our models. I think we have a model.
I think there probably is. I'll dig it out for next class. Yeah.
In there.
so you guys can play around with it, but certainly better than my diagram. So as I said before, because these are the most common elements, in the Earth's crust, you also tend to get the most common minerals from these silica tetrahedron. The feldspars, most common mineral in the Earth's crust, are silicate minerals. Quartz is a silicate mineral. Olivine is the most common mineral in the Earth's mantle, upper mantle at least. All of these are silicate based. So if you're not familiar with the tetrahedron, go back and look at these diagrams and get a little familiar with it. As I said a second ago, very strong bonds. As you guys mentioned, it requires an awful lot of energy to break these bonds. So for that reason, these magmas are very hot. Now, melting is an interesting process. If you go to take your basic chemistry course, a lot of times they talk about melting is when you break all the bonds and you turn it into a liquid. Because these bonds are so strong and because they require so much energy, a lot of times out in nature, they just sort of barely melt. They don't completely melt. You break some bonds, but not all of them. As it turns out, this is probably one of the most important concepts we'll go through because it really affects how volcanoes behave. If you melt something thoroughly, how will that melt be different than something that's only melted enough so that some bonds break? So if you have a rock, you apply heat to it, and you start breaking a few bonds. Enough to break down the solid structure of it and let each component start to move, okay? Now compare that to a situation where you add so much heat that basically all the bonds break. How are those two liquids going to be different? Their ability to flow. What is the property of a fluid? What's the property called that describes a fluid's ability to flow? Viscosity. Yeah, something that has a high viscosity. You can think of viscosity and fluidity as being opposite. So if something is highly viscous, it doesn't flow very well. It's got a low fluidity. High viscosity, low fluidity. Low viscosity, it's high fluidity. So if you melt something a lot, it's going to have a very low viscosity. It's going to flow very easy. Something like the lavas that we get in Hawaii. Those things flow great. If you don't break those bonds to that extent, then it's not going to flow as easy. It's going to be really stiff and pasty. The lavas that come out at Mount St. Helens and most of the continental volcanoes are millions of times more viscous than the lavas that we get in Hawaii. I've stood on top of lava flows that have moved, and you think, wow, that sounds kind of cool. It's not. It's about as fun as watching grass grow. There's a volcano in Central America, the one I talked about earlier, that I did my hazard assessment on, Santiaguito. I went there back in the 1990s several times, and there was a lava flow coming down, and it would move about this much in a day. Glacial. So the top would completely cool and it'd have a nice hot core. So you could walk around on top of it. It was pretty warm. But, you know, the whole thing would move this far in a day. And you'd sit there and eat lunch and you're definitely not feeling the movement. But every once in a while you'd see a rock shift. That was about the only indication that anything was even going on, is you see a rock shift now and then. But yeah, it's so viscous that it just barely moves. Think about a gas bubble that's trapped in a really viscous magma. What does that gas bubble want to do? What's its only passion in life? Escape. It wants to rise up because it's less dense than its surrounding, right? Can it rise up if the lava is really viscous? No, so these gas bubbles form deep within the earth, okay? And they can't escape. Think about how much pressure must be in a gas bubble to withstand all of the squishing. Let me just draw a quick little diagram here. So if you have the Earth's surface here, and you are down in a magma chamber, let's say 4 kilometers deep. Okay, here's your magma chamber. You have a bubble down there. In order for that bubble to stay open, it has to push on the environment as much as the environment is pushing on it, right? And it's being pushed down with all this rock. I mean, we could do this experiment. We could go out in the grass somewhere and dig a hole 4 or 5 feet deep, and I could throw one of you in it, and I could bury you with 4 or 5 feet worth of dirt, and it would feel heavy, right? What if I dug that hole 30 feet deep and filled it with rock? It starts to get crushing, right? What if I was down there 2.5 miles? It's ridiculous, right? But yet that little bubble has to stay open. So it has to have equal amount of pressure going back. What if this moves up to the surface and that bubble can't get out?
Does it start to expand as it moves up?
It's going to try to expand, right? But the only way it can expand is if the magma moves. Then this magma is too stiff, so it doesn't move. It doesn't really grow. So when it gets up to the surface, it hasn't expanded very much because that liquid around it is just too damn stiff. So what's the pressure inside of it?
Probably really high.
It's ridiculous. So by the time it gets to the surface, there's so much pressure being exerted by the bubble on the surrounding magma that it actually starts to shatter the magma. And you've seen volcanoes that have these tremendous ash eruptions. That's exactly what's going on. The bubbles are bursting the magma, and then that gas is jetting it 100,000 feet into the atmosphere. And it's all because this magma is just too damn stiff to move out of the way so the bubble can grow. So it arrives at the surface with enough energy that it's one little tiny bubble would have more energy than a gunshot. And you've got billions of these things all arriving at the surface at the same time. So they basically rip and explode the magma to pieces. And that's how you get volcanic explosions. That's what makes ash. That's what makes pyroclastic flows. So this behavior has a lot of sort of consequences to it. Here's one way to think about it. So we start with a solid mineral on the left, and we add heat, and we start to break bonds, okay? If we add more heat, what happens? More bonds break. We add more heat, more bonds break. The more bonds that break, the more fluid your magma is. You go to Hawaii, the magma there is very fluid. If you're a bubble, what do you want to do? There are bubbles in Hawaiian magmas, but they want to rise, right? Because that magma is so fluid, they can rise. And they can escape before they get to the surface and rip the magma apart. So you don't get explosions in Hawaii. Instead, the lava, the magma, is fluid enough that all the gases are able just to bubble out of it, and it arrives at the surface all degassed, and it just flows out in these nice red runny lava flows that you don't have to worry too much about. You don't have to worry about it blowing up in your face. But the more viscous magmas tend to be more explosive. So the hotter the magma, the more broken down these silicate minerals get, and the more fluid the magma is. All right, I think we're going to stop with that. Still the same time as when we started class. So we will call it quits for today. That's enough for the first day. This next section is going to take a little longer than we have remaining, so we'll just start it up again next week. If you have questions, I'll stick around. And if not, I will see you guys next week.